Hello, welcome to 241 Material Science. Today we're going to discuss creep. Creep is also known as cold flow. It is slow, progressive. Progressive means increasingly continuing and time-dependent deformation of a material under a constant mechanical stress. It can occur as a result of long-term exposure to high levels of stress that are still below the yield strength of the material. It is more severe in materials that are subjected to heat for long periods, and it generally increases as they near their melting temperature. But creep can also happen at room temperature in certain materials, for example, lead, glass, albeit much slower. Creep results in a time-dependent increase in length, which could in turn be dangerous while in service for certain applications. And actually, we do creep tests and we measure dimensional changes at constant high temperature and constant stress. And these creep tests are useful for modeling long-term applications which are strain limited, providing prediction of life expectancy before service. For example, a turbine blade uh, would be a strain in a turbine blade would be very critical. And these creep tests are actually very long. They took around 210,000 hours. Actually, it's even longer for concrete, but I'm not going to discuss creep in concrete. Creep generally occurs at elevated temperatures, so it's common for this test to be performed with an environmental chamber for precise heating or cooling control. Temperature control is critical so that we minimize the impact of thermal expansion on the sample and we only focus on creep. Here is a creep apparatus. Basically, you have your sample, and around the sample, you have something like an insulating box or heating box, and to keep the actually temperature constant. So the general procedure is first you have an unloaded specimen and you heat it to a required temperature, and you measure the gauge length. The predetermined load is applied quickly, uh, and then a measurement of the extension are observed at frequent intervals for a very long period of time. Eventually, what we get is a typical creep curve is given here. Eventually, what we get is a creep curve, and a specimen subjected to a constant stress at constant temperature, and the extent of deformation is measured in terms of strain, and we basically plot the resulting data in a creep strain time curve. A creep curve has actually four main stages. The first stage is the instantaneous deformation. The second stage is your primary transient creep, and then we have a secondary or steady state creep, and then last we have tertiary creep, and the curve ends with rupture of our material. Rate of deformation is called the creep rate because the slope of the line in the creep strain versus time curve. Slope of the curves are used to determine the material constants. Generally, three or more stress levels are used for discrepancies in lab data. So you just don't measure one or two curves to obtain material constants, but rather you take three, four curves. So let's go through stages of creep curve. The first is instantaneous deformation. It is mainly elastic. The second is primary or transient creep. It starts with a rapid rate and it slows with time. It is a decreasing rate because of work hardening. It is kind of similar to delayed elasticity or retarded elasticity, and the deformations in this stage are recoverable. The secondary stage, or also known as steady-state creep, this is the longest stage with relatively uniform creep rate. Actually, at this stage, your material has essentially a viscous character. There is a balance of work hardening and recovery. Steady-state creep rate is the most important parameter of the creep behavior in long life applications. It is highly temperature sensitive and can be related to temperature with an equation similar to that in viscosity. Here in the equation, A and N are material constants. E is the activation energy for creep, R is the gas constant, and T is the absolute temperature. The last stage is the tertiary creep. It occurs at an accelerated rate and terminates when the material breaks or ruptures. It is associated with bone necking and formation of grain boundary walls. Time to rupture and a stress relationship can be estimated with the given formula. Here, Tr is time to rupture, A and N are material constants. There is a concept called rupture lifetime TR. Sorry, I didn't mention what it is. It is the total time to rupture. So from a creep test, there are two very critical parameters that we check. The first one is the steady state creep rate. This is an engineering design parameter for long life application. And the second we check is the rupture lifetime. Relatively short life applications actually utilize rupture lifetime. So let's solve some questions. Please, after reading the question, pause this video and try to solve it yourself. The following creep data were taken on an aluminum alloy at 400 Celsius and a constant stress of 25 megapascal. Please plot the stress strain versus time graph and determine the steady state or minimum creep rate. And here, initial and instantaneous strain is not included. So we have a measurement up to minute 30. We have our creep strain, and please plot the data and determine the steady state or minimum creep rate. Okay, let's see what you have done. Here is the plot. The steady state creep rate is the slope of the linear region. And we actually draw a straight line. Basically, I show it with a red line superimposed on the curve, and you check roughly the slope of it. I use the points given in the table. So 0.153 minus 0.092, it is divided by 18 minus 10. So it roughly gives us 0.0076 per strain per minute as our strain. Okay, I hope you did it. You solved the first question. Let's do a second question about steady state creep rate. A specimen of 760 millimeter long of an alloy is to be exposed to a tensile stress of 80 megapascal at 815 Celsius. Can you determine its elongation after 5,000 hours? Please assume that the total of both instantaneous and primary creep elongation is 1.5 millimeter. So please stop this video and try to solve it yourself before watching the solution. So the 815 is the red one, and the y-axis is stress, and x-axis is the steady state creep rate. So let's go through the solution. First thing is first, let's check 815 Celsius and 80 megapascal. So the vector is 815 Celsius. And when we check 80 megapascal, actually we can read the steady state creep rate as 5.5 times 10 to the minus 6 per hour. So the steady state creep strain actually is steady state creep rate times time. So we already calculated 5.5 times 10 to the minus 6 per hour as our steady state creep rate. So we multiply this with 5,000 hours and we get our steady state creep strain as 0.0275 at 500 hours. So let's calculate the steady state elongation. So it is strain times original length. So 760 millimeter times our strain at 500 hours, 5,000 hours, it is 20.9 millimeter. So total elongation would be our change in length plus the instantaneous and primary creep elongations. So 20.9 plus 1.5, we will get 22.4 as our final elongation. Let's solve another question. For a cylindrical alloy specimen, originally with a 10 millimeter diameter and 505 millimeter long, what tensile load is necessary to produce a total elongation of 145 millimeter after 2000 hours at 730 Celsius? Please assume the instantaneous and primary creep elongation as 8.6 millimeter. Please pause your video before continuing. Here, 730 is the green curve. Okay, let's see how you have done. So we want 145 millimeter after 200 hours, sorry, 2000 hours at 730 Celsius. So we check our green curve now. Steady state elongation basically is total elongation minus instantaneous and primary creep. So we know our total elongation is 145 minus 8.6. It will give us 136.4 millimeter as our steady state elongation. And we know that this is our strain times our initial length. So it is basically strain times 505 millimeter. So from here, actually, we can calculate our steady state creep, which is calculated at 0.2728. So now that we know our steady state creep strain, it is actually time times a steady state creep rate. And we know time is 2000 hours. So we can calculate our steady state creep rate as 1.35 times 10 to the minus 4 per hour. And our stress can be calculated now from the graph. The green curve represents 730 Celsius and check 1.35 times 10 to the minus 4 per hour. So it will give us approximately 200 megapascal as our stress. And the question actually asks for the load. So we know the stress, it is 200 megapascal. We multiply it with the area of our sample, and we will get 15.7 kilonewton as our tensile load for this test. Okay, one question, one more question. And if a component fabricated from an alloy is to be exposed to a tensile stress of 300 megapascal at 650 Celsius, can you estimate its rupture time? Please pause the video before watching the solution. 650 Celsius is the blue curve. Here, x-axis gives you rupture lifetime and y-axis gives you your stress value. So we are at 300 and we are at 650 Celsius. Of course, reading from these curves, they may not be exact, so but at least you can get a ballpark picture. Okay, so what we do is basically we have our temperature 650. We know we're at 300 megapascal, and we read our plot. So it is here 10 to the 2 times 1, 2, 3, 4, 5, 6. So 6 times 10 to the power 2, it's 600 hours is the rupture lifetime. So let's go through effect of temperature and applied stress. Actually, both the temperature and applied stress adversely affect the creep strains. At temperature is substantially below the melting temperature, they're below 0.4 times melting temperature. And after the initial deformation, the strain is virtually independent of time. And here on the graph, you can see it as the orange curve. So it is a temperature that is relatively low. It is basically 40% of the melting temperature is below that. And after the initial deformation, pretty much continuous. And it's virtually independent of time. But with increasing stress or temperature, you observe some changes. First of all, the instantaneous strain at the time of stress application increases. The steady state creep rate increases and rupture lifetime decreases. So let's go over steady state creep rate question. So please also pause your video before answering this question. And in the Scripps test of an aluminum alloy, we are now at 180 Celsius. We apply various stresses and we check the steady state creep rates. And for 62 megapascals, we observed as 0.0066 per hour as our creep strain rate. And for 55 megapascal, it is 0.0025 per hour. And the question says, can you determine the steady state creep rate for 59 megapascal? We know at that stage, at steady state creep rate, it can be estimated with this particular formula where A and N are material constants. And actually, because we are using constant temperature, this formula can be simplified a little bit because A doesn't change, temperature doesn't change, and E and R are constants. So basically, it can be written as beta times stress to the power N. So try to solve it yourself before continuing, please. Okay, so let's solve it together. We know what we have at 55 megapascal and what we have at 62 megapascal. So basically, we can, from these two equations, we can calculate two unknowns, beta and n. How do you solve these kind of actual equations? What I do is I divide them to each other. So the 0.0066 divided by 0.0025 would be equal to 62 to the power n divided by 55 to the power n, because betas will cancel. And this equation can be written as ln 2.64. 2.64 is basically 66 divided by 25 equals to n goes outside, so n times ln 62 minus n times ln 55. So basically, to solve this equation, I took ln of both sides. So from this equation, I can solve n as 8.1. And I use this value in one of the two equations that I know. So beta is calculated as 2 times 10 to the minus 17. So now I know n and beta, and I can actually calculate the steady state strain rate for the 59 megapascal case. It will be beta times 59 to the power n, and it will be 0.0044 per hour. Actually, let's go over the factors affecting creep characteristics of metals. These include melting temperature, elastic modulus, and grain size. Basically, of course, this is a generalization, but higher the melting temperature, greater the elastic modulus, larger the grain size, and better materials resistance to creep. Relative to grain size, smaller grains permit more grain boundary sliding, which results in higher creep rates. This effect may be contrasted to the influence of grain size on both mechanical behavior at low temperature and increase in both strength and toughness. Metal alloys that are especially resistant to creep have high elastic moduli and melting temperatures. These include the superalloys, stainless steels, and refractory metals. Okay, let's solve one final question. Can you calculate the lifetime of a slip cast MG or refractory at 1300 Celsius and 12.5 megapascal if 1% total strain is permissible? Slip cast is basically when you have a ceramic, it's a ceramic forming technique for pottery and other ceramics. And it's especially useful if the shape is not an easy one to make on a wheel, pottery wheel. And in slip casting, a liquid clay body slip, usually mixed in a blender, is poured into plaster molds and allowed to form a layer that cast on the inside walls of the mold. And after solving part A, please repeat the calculation for hydrostatically pressed MgO refractory. And hydrostatically pressing is basically a method of compacting powdered materials into a solid homogeneous mass before machining or sintering. So these are two different methods of making similar shaped objects. And comment on the effect of processing on the relative performance of these two refractories. And on the table, actually, we have the creep data, rate data for polycrystalline ceramics. Here we have MgO slip cast and MgO hydrostatically pressed. And the MgO slip cast as a creep rate as 330 as 330 as our strain rate. Of course, these are 10 to the power 6 divided by hour, and the hydrostatically pressed one has 33 10 to the power 6 per hour. So please pause the video before continuing. And the part C is actually very difficult. Can you comment on the effect of processing on the relative performance of these two refractors? So please pause the video before actually solving this question. Okay, let's solve it. So part A says calculate lifetime of a slip cast MgO refractory at 1300 and 12.4 megapascal if total strain allowed is 1%. So from the table, we know the creep rate is 330 times 10 to the minus 6 per hour. And although this straight line is actually valid for the secondary stage of creep, it dominates the overall performance. So we will assume that we can use it for the entire lifetime with some, of course, negligible error. So total strain is basically strain rate times time. So time is, we have total strain, we divide it with strain rate. So we know the lifetime is time to 1% strain. So total strain is 0.01. We divide it with our strain rate, and lifetime is 30.3 hours for the slip cast MgO. And let's repeat the calculation for hydrostatically pressed MgO. And hydrostatically pressed MgO has a creep rate of 33 times 10 to the minus 6 per hour. And again, this creep rate, this strain rate actually is only valid for the secondary stage, but we will assume that we can use it for the whole range. So again, we want to get our lifetime, which will be time to 1% strain. So it is 1% strain divided by 33 times 10 to the minus 6 per hour. It will give us 303 hours. So one was 33, and this is 30.3, and this is 303, so tenfold. And let's comment on relative performance of these two refractories. Hydrostatic pressing produces a more compact, less porous microstructure. In general, less pores in the ceramic gives superior properties. In this case, less pores render the material less susceptible to creep deformation. Okay, thank you very much for listening to this lecture. We will continue in our next lecture with fatigue. Bye.